Good morning. For thousands of years, the geocentric model of the solar system was considered to be correct. Bo, what is the geocentric model of the solar system?
Flippin' physics.
The Earth would be at the center of the solar system, with the Sun and the other planets revolving in circles around the Earth.
Thank you, Bo. The geocentric model was formalized by the Greek astronomer Claudius Ptolemy during the 1st century of the Common Era. Roughly 1400 years later, in 1543, a Polish astronomer named Nicholas Copernicus proposed a heliocentric model with the Sun at the center of the solar system instead of the Earth. A few decades later, a Danish astronomer named Tycho Brahe made accurate and comprehensive observations of the locations of planets and hundreds of stars in the night sky. He did these observations for 20 years before his death in 1601, and they were all done without a telescope because the telescope was not invented until the early 1600s. After Tycho Brahe's death, his assistant, Johannes Kepler, a German astronomer, analyzed Tycho Brahe's data for roughly 15 years and derived mathematical descriptions of planetary motion, which are now known as Kepler's 3 laws of planetary motion. Today we are going to discuss Kepler's first law of planetary motion. Bobby, please read it.
Kepler's first law of planetary motion states that planets move in elliptical orbits with the Sun at one focus. That seems kind of straightforward.
Yeah, to us, more than 400 years later, the fact that planets move in elliptical orbits with the Sun at one focus does seem rather obvious. However, considering that people thought the Earth was the center of the solar system for thousands of years, it was a remarkable conclusion based on observation.
Absolutely.
Yeah, sure.
All right, let's draw an ellipse. We start with a piece of cardboard, 2 thumbtacks, a piece of string tied in a loop, and a writing utensil. We can place the 2 thumbtacks, which become the foci of the ellipse, and by looping the string around the 2 foci, we can use a marker along with the looped string to draw an ellipse. And then redraw the ellipse to make it darker. And there you have it, an ellipse with the 2 foci where the thumbtacks are. This represents the elliptical orbital paths of all satellites, where the satellites follow the path of the ellipse. The central body, or the object the satellite is orbiting, is located at one focus, and there is nothing located at the other focus. And now let's switch to a more accurate ellipse I used the computer to create. I have added an XY coordinate system to help identify parts of the ellipse. The 2 foci are labeled f sub 1 and f sub 2. The elliptical curve is drawn such that the sum of r sub 1 and r sub 2, the distances from the respective foci to the elliptical curve, is constant. In other words, r1 plus r2 equals a constant number. That was the purpose of the string. That is how we physically made r1 plus r2 equal a constant number because the length of the string was constant. The major axis is the longest distance through the center, which also passes through both foci and is the distance 2a, where the distance a is called the semi-major axis. The minor axis is the shortest distance through the center, and it is the distance 2b, where the distance b is called the semi-minor axis. And each focus is located a distance c from the center of the ellipse. Unfortunately, not all textbooks agree on which letters to use for these distances in an ellipse, so...
Fun.
Yeah.
So R1 plus R2 equals the major axis, 2A, right, Mr. P?
Billy, that is correct. Now that we have defined the major axis, we can identify that the sum of the 2 distances from each focus to any point on the ellipse equals the major axis. I also want to point out that at the location where the ellipse intersects the y-axis, the 2 distances from the foci to the ellipse are equal in value and are also equal to a, the semi-major axis. That means, for an ellipse, c squared plus b squared equals a squared.
I thought a squared plus b squared equaled c squared.
This is not the Pythagorean theorem.
It is the definition of an ellipse.
Those are 2 different things.
They sure look similar.
Yeah.
Yeah, that is unfortunate. For an ellipse, c squared plus b squared equals a squared. Let's define the eccentricity of an elliptical orbit. Eccentricity, lowercase e, equals c, the distance from the center to one focus, divided by a, the semi-major axis. Eccentricity basically describes how circular an ellipse or an orbit is. Bobby, what is the eccentricity of a circle?
The eccentricity of a circle. Well, for a circle, the distance c equals 0 because the two foci are both in the same location in the middle of the circle. That means the eccentricity of a circle equals 0 over a, or 0.
Correct. The eccentricity of a circle equals 0. And if c equals a, which is an eccentricity of 1, then b equals 0, and the ellipse is actually just a line segment. Therefore, the range of eccentricities for an ellipse are between 0 and 1. And here are the eccentricities of all 8 planets.
I miss Pluto.
As you could see, the planet with the largest eccentricity is Mercury at 0.2056. To understand what an ellipse with an eccentricity of 0.2056 looks like, this is a circle, and this is an ellipse with an eccentricity of 0.2056. Clearly, that is nearly the same as a circle, which is why we often approximate planetary orbits as circular.
How can that illustrate an ellipse with an eccentricity of 0.2056? It should be squished and more like an oval, right?
Actually, we could figure out if that makes sense.
How?
Well, we know eccentricity equals c over a, so with an eccentricity of 0.2056, c equals 0.2056 times a. We also know a squared equals b squared plus c squared, so b squared equals a squared minus c squared. Substitute 0.2056 times a in for c. 0.2056 squared equals 0.042271. So b squared equals 0.95773 a squared. And we get that b equals roughly 0.98 times a. In other words, for the elliptical orbit of Mercury, the semi-major axis B is 98% the size of the semi-major axis A. That is why it pretty much looks like a circle.
Oh.
Yeah. Thanks, Bo. So that is Kepler's first law of planetary motion. In our next lesson, we will learn about Kepler's second law of planetary motion.
That seems logical.
Thank you very much for learning with me today. I enjoy learning with you.